And now we are given that modulus of z, a variable complex number, minus z1, a fixed complex number that is represented by point P on the Argand diagram, and z minus z2, which is represented by Q on this Argand diagram. So what we have here is actually a perpendicular bisector of P and Q. And since P and Q is also the chord of this circle over here, so the perpendicular bisector will definitely pass through the center of the circle. What we are supposed to do is to find the complex number that these 2 points are representing, and to do that I'm going to add in two triangles, and the two triangles will be this and this. Let me draw this out. From here I'm going to extend a vertical line downwards, and then a horizontal line to the center of the circle, and this will be 90 degrees. I'm going to do the same thing for the other triangle that I'm trying to form, a horizontal line and then a vertical line downwards, and this is going to be a right angled triangle. And what I can now see is that for this big triangle here, let me do a quick sketch. For this big triangle, this angle is alpha, and here is 90 degrees. As for this angle, I'm going to call it theta. And what I'm going to do is I'm going to compare this angle to this angle over here for this triangle. So for the other triangle, let me sketch it here. So this will represent this triangle, 90 degrees. And like what I was saying, I'm going to try to compare this angle to this angle and their corresponding angle, which means that this angle will be theta. And if this is 90 degrees, this is theta, this is 90 degrees, and this is theta, which means that this angle here must be the same as this angle, alpha, which means that on this triangle, this angle here is alpha. And this will be the same as this angle, and since this is 90 degrees also, which means that this angle here will also be alpha. And since this distance is the radius of the circle, which is 1, so here is 1, here is also 1. As for alpha, I can refer it to the information that is given to me by the question. Tangent alpha is 0.4, which is 2 over 5. If I were to sketch a right angled triangle to represent this angle alpha, so if this is alpha, that means it is going to be 2 here and 5 over here. By applying the Pythagoras theorem, this is going to be the square root of 5 square plus 2 square, square root of 29. Which means that if I were to reference this vertical distance to alpha and 1, this distance here is actually 1 cosine alpha. And from here, cosine alpha is 5 over square root of 29. So this distance is 5 over the square root of 29. And this horizontal distance, using this triangle again, is 1 multiplied by sine alpha. And according to this, sine alpha is 2 over square root of 29. With this information that is given, we can now quote the complex number that this point is actually representing, which for the real portion, I'll reference it to 3. So it is going to be 3, and I'll go back by this distance to go to this coordinate, and this distance is this. So it will be 3 minus away 2 over square root of 29. And the imaginary portion will be 1, since the y coordinates of this point is 1, plus this distance, so it will be 1 plus 5 over square root of 29. For the other point, which is this point here, I'm again going to reference it to the center of the circle, so the other one will be 3. So from here to here is 3, then I'll plus this distance. This distance is the same as this distance, so it will be 3 plus 2 over square root of 29. And for the imaginary portion, it is going to be the y coordinates of this point, which will be 1 minus away this distance, which is the same as this distance. So it will be 1 minus away 5 over square root of 29.